So let us continue with Macaulay's method. So now you have another type of load, and that is a uniformly varying load. So let us say this is your uniformly varying load. And this is having a certain magnitude. Let us say this is 6 meters and this is 4 meters. Let us say the magnitude is 60 Newton per meter, the maximum magnitude. And this is A, this is C, this is B. And let us assume that, means probably I need to assume at this stage that you can find out RA and RB. So RA is known to you. So let us take an element which is located at a distance x. So the equation for M now is RA into x minus, now you are having a certain portion of the uniformly varying load. So when you are having a certain portion of the uniformly varying load, you have to take moment for that portion only. So this what is, means you need to first calculate, this is the area under the triangle. So area of the triangle maximum height was 60. So obviously here the height of the triangle is 0. At 1 meter the height is 10 Newton per meter. At 2 meters it is 20 Newton per meter. At 3 meters it is 30 Newton per meter. So as you go from x is equal to 0 to x is equal to 6, it starts from 0 and finishes at 60 Newton per meter. So you need to find out the instantaneous height. So first is area under the triangle will denote the total load. So you need to first find out area under the triangle. So area under the triangle, half into base into altitude. So the base is x minus 4. This distance is actually x minus 4. So half into base into altitude. Altitude is the instantaneous height. So the instantaneous height, it is 60 by 6 is per unit increase. 60 by 6 is per unit increase in height. So for a distance of x minus 4, there will be a certain increase. And this entire component is your area under the triangle. So this denotes area under the triangle, means this is the total load. Now this total load has to be multiplied by a perpendicular distance, then you will be getting the momentum. So you, wherever you are standing, you will always be standing at the larger end. So when you are standing at the larger end, it is L by 3. So L now is x minus 4 divided by 3. Okay, so this entire term will stand in separators because this is distance parameters. So if you write down, this is actually RA into x. If I forget separators somewhere, that does not mean that it need not be written. It has to be written. So this is half into 60 by 6 multiplied by x minus 4 whole cube by 3. Okay, so if you look at this term, you can very well understand that it is now initially a cubic function. So half is for area under the triangle, 60 by 6 is maximum height divided by the total length multiplied by this term is x minus 4 whole cube by 3. So this, now you have formed the equation for moment. Now this is your final equation for moment. Again you need to put it, equate it to d2y by dx2 is equal to m. Integrate twice. Put down the boundary conditions. Put boundary conditions. The boundary conditions are x is equal to 0, y is equal to 0, x is equal to L, y is equal to 0. These two will enable you to find out C1 and C2 and find x at dy by dx by putting dy by dx is equal to 0. Uh, so this will give you, if you put, this will give you to find y max and put specific values, specific x to get y at definite locations. Okay, so this is the entire process. Now, coming to different adjustments that you need to make in these problems. So, let us say this is again a simply supported beam and it has been loaded like this. This is 60, this is 6, and this is 4. Let this be RA, this be RA. Now, you want to solve this problem. This problem needs to be solved starting from x here. You have to take x from here. Okay, so the equation will be written in terms of RB into x. The reason is, if you are starting from here, you will always encounter a triangle and things are known for triangle. If you look at the same problem and you try to solve it from the other side, so if you try to solve it from this side, what happens is, if this is x, now this is a trapezium. So it is not that area of a trapezium cannot be found out, but the system will be getting difficult. So it is advisable that whenever you have a loading condition like this, then start from the side where you end up at a triangle. You should not end up at a trapezium, because if you end up at a trapezium, the problem will be getting very difficult. Means it is not that you cannot solve it. Everything can be solved. You know how to find out the centroid of a trapezium. You know how to find out the total area under the trapezium. Things are not impossible, but unnecessary. Why to make the problem difficult? So it is advisable that you do not follow this practice and you follow this practice. That take x from the end where you end up at a triangle, you do not end up at a trapezium. Now, another situation, these are, this is one. Now, as you have seen in the case of a uniformly distributed load, that if the load does not extend up till x is equal to L, you need to extend it, add a certain amount of load so that x extends up till L, and deduct the same amount of load and form the equation. Now, suppose the problem also comes out to be here. So this is 2 meters. Let us say this is 6 meters. This is again 2 meters. This is 60. Now, if you have a state like this, now here x is not, the uniformly varying load does not extend up till x is equal to L. Means if you take a section here, you will not be having this load. So it will be very difficult to interpret this amount of load. So what you need to do is you need to add a load and you need to subtract load. Okay. So if you are adding and subtracting load, obviously what will happen? This beam will change to this situation. Now this is at 6 meters it was 60. So if you have extended to another 2 meters, this has become 80 and this is 8 meters. This is 2 meters and this is 8 meters. So this is very well justified that at every 1 meter it was increasing by 10 Newton per meter. So you have added another 2 meters. So this 60 has now become, because it is a uniformly increasing load, so this has become 80. So this triangle will be solved. Now the problem that has come out of this equation is that you have actually added a trapezium. You have actually added a trapezium. You have not added a triangle. If you look at this structure, you have added this portion. And this portion is a trapezium, it is not a triangle. So when you are putting into the top of the beam, it is very easy to interpret. Now, at the bottom of the beam, you need to understand that how much have you actually added. So you have actually added how much. You need to represent it like this. This is 60, this is 80. Okay, and this is 2 meters. So this is what you have done to your problem, that you have added, or you have gone on increasing the triangle. And here what you have done is you have added a trapezium. Actually, if you isolate this portion, this becomes a trapezium. So you need to add this trapezium or subtract it. So this is your final figure. Now you need to write down the equation for this. So let us take an, obviously, just in the case of uniformly uh, varying distributed load, that it may start from anywhere, but it has to end at x is equal to L. This is the necessary condition so that the equation of M becomes valid. So let us take an element, let us say it is here somewhere at a distance x. So the equation, let us write down the equation for M. So M is Ra into x. So if I forget separators, take it for granted that you have to write it. Minus half into 80 by 8, because this is the total height, 80, and divided by the total length at which it has been applied, and it is x minus 2 whole cube by 3. This is the top portion. Now come to the bottom portion, which have now for the bottom portion, what you need to do is this trapezium, don't treat it as a whole, treat it into two parts. Now this rectangle denotes a uniformly distributed load, and this triangle denotes a uniformly varying load. This uniformly distributed load, it starts from x minus 8. So this is how much? It is 60 into x minus 8 whole square by 2 plus. Again, you have this uniformly varying load. So this height is now 20. If this is 60, this is 80, and if you have drawn a parallel line, that means you have now a triangle of 60, 60. 60 into 2, you have a rectangle. So if you have a rectangle, this 60 into 2 is isolated. So this instantaneous height is 20. And wherever you are, you are at the larger end. ठीक. So again it will be half into 20 by 2. This is 20 by 2 and into x minus 8 whole cube by 3. So the amount of load that you have added, you have subtracted the same amount. Okay, is it clear? So this is your total m equation. Again, the process remains the same. You can go on adding and subtracting and put down the boundary conditions and find out. So these types of problems, they actually go on getting very difficult and difficult. So till date, as far as university syllabus is concerned, I have not seen this type of problem. Neither in most of the books also, these types of examples have not been quoted nor they have been discussed. But you need to know, because you know how to draw the bending moment diagram of all these types of loads. So you should also know to interpret these equations in terms of m, and you need to know the general equation of m, and you also need to know how to find out the deflection. Okay, so I'm rubbing it. Now come to the last type of load. So last type of load, if you look at the last type of load, it is a constant moment. Let us say this is of magnitude m. So RA and RB, I believe you will be able to calculate. Let us say this is at a distance of 6 meters, this is a distance of 2 meters. Now you need to write down the equation for it. So to write down the equation for it, what you are doing is, let us take an element which is located at a distance x. So m becomes equal to RA into x minus, this is of magnitude m and it is acting at a distance of 6. So this is x minus 6. Now this x minus 6, if it is m into x minus 6, what will happen? This is moment into again a distance. So it will not be technically correct. But if you do not write x minus 6, the problem is, how will you understand that until and unless you reach x is equal to 6, this moment will not be taken into consideration. So you need a distance parameter always, because that distance parameter is actually guiding you whether you have reached at that point or not. So what we do here is, we write it to the power 0. So for a constant moment, this is the method by which we represent it. So this is written as x minus 6 to the power 0. Okay. And if you integrate it, let us say we equate this to ei d2y by dx2 is equal to m, and integrating twice. So the process of integration is as usual. This will be ei dy by dx. This will be written as Ra into x square by 2 minus m into x minus 6. This will be written as like this, plus C1, and EIY will be written as RA x cube by 6 minus m into x minus 6 whole square by 2 plus C1x plus C2. Put down the boundary conditions, calculate C1 and C2. This is the shortcut for this is the methodology for representing moments, constant moments, in bending moment equations. Okay, so you need to understand this, and then only uh, you will be able to solve them. Now, this means that we have now incorporated all the different types of loads that can be created or that can be applied on a beam, for which you can write the bending moment equations. So this completes all different types of loads. Now we'll be completing different types of beams. Now let us come to overhanging beams. So you know all different types of loads. The difference lies in boundary conditions. Difference lies in boundary conditions means that it may have one or two overhangs. Let us say that this is an overhanging beam, and you have this is 6 meters and this is 4 meters. So whatever load has been applied on it, let us say it is a point load and a uniformly distributed load. This is of 10 Newton per meter and this is of 20 Newton, and this is 2 meters. So obviously this is 4 meters, and you need to write down the equation for it. So this is RA and this is RB. So if you look at this beam, this is an overhanging beam. So the concept still remains the same, that it has to extend the load, uniformly distributed load has to extend till x is equal to L. Now x is equal to L. The understanding is not that L is not at the support. L is the total length of the beam. So the total length of the beam is 10 meters and the supports are located 6 meters apart. So that means you have to add and subtract load. So you need to add this much amount of load and you need to subtract this much amount of load. Okay. So if you write down the equation for it, I believe that you know RA, how to calculate RA and RB. So this is, let us take an element at a distance x. So this is RA into x. I'm writing the equation for M, minus 20 into x minus 2. Now this total UDL minus 10 into x minus 2 whole square by 2. Now you have RB also. So you have plus RB into x minus 6, and you have added this, subtracted this much amount of load. So again this is plus 10 into x minus 6 whole square by 2. So this is your final equation of moment. The difference as compared to a simply supported beams lies that you need to integrate it twice and find out the value of C1 and C2. At x is equal to 0, y is equal to 0, and at x is equal to 6, you have y is equal to 0. At x is equal to 6 means at this location y is 0. Earlier it was the ends of the beam, now it is some point where the supports have been located. So what you could understand or figure out till now was that this x is equal to 0, x is equal to 6, they are not the ends of the beam, they are the location of supports with respect to x. And again the process remains the same, find out dy by dx, at which you can say that the y will be maximum. So put equate dy by dx is equal to 0, we'll be getting a certain value of X in terms of L, and that needs to be utilized for finding out the maximum deflection at a certain location. Okay, so this is all about overhanging beams, loads, only we needed to discuss the boundary conditions which are different, which are slightly different as compared to a simply supported beam.